graduate student in the Kurti group, and I study synthetic organic chemistry. And today I want to talk to you guys about the development and applications of nitrogen transfer reactions. So while you all see these images as common consumer products, from cleaning supplies to dyes that can color our clothes and pharmaceuticals to cosmetics, instead, as a synthetic organic chemist, what I see are the chemical compositions and molecular structures that make up the active ingredients in each of these products. So these are much more complex, and today I want to show you how we can take everyday items and see how the chemistry impacts the world around us. So as an organic chemist, I like to think of chemistry as having two main subsets. First, there is methodology development that specifically focuses on creating a fundamental chemical understanding. So this is kind of like building a house. We take tools and we construct a foundation to understand chemical reactivity patterns. And then the hope is that other scientists will use this knowledge toward the pursuit of a natural product or pharmaceutical target. So in chemistry terms, this will be like focusing on one specific reaction. This is the Diels-Alder reaction. And the main motif of this is that we form two new bonds to carbon atoms in one step. So one chemist in my research lab may spend a significant amount of their time just studying this single reaction with the hopes that other chemists can utilize it in applications. So instead, we also have natural product synthesis. So in this, scientists can go out into nature. So for example, we have the Pacific yew tree, known as Taxus brevifolia, and they can extract important chemical compounds from its bark. So from this we get Taxol, which many of you may be familiar. It's a very effective breast and ovarian cancer treatment. And so in order to make sure that we don't have to cut down all of the trees in the ecosystem to get this really important drug, we like to build up in the lab, starting from cheap and readily available materials, to create this structural complexity. So for Taxol, it takes about 10 kilograms of Taxol to get 10 grams of dose. So it's about 1% yield. So it's good that we can make these synthetically so that all of the people can take this drug to get better. So when we look at a chemist's toolbox, organic chemistry focuses around two main atoms, carbon and hydrogen. But in my research, in addition to these, what I like to look at is how we insert nitrogen into various systems. So now your main question probably is, why nitrogen? So the amount of money that's spent on the pharmaceutical and biotechnology research and development is very high. And nitrogen plays a role in this because there are about 2.8 nitrogen atoms in every drug that was approved by the FDA in 2010. So while this may not seem like a lot of nitrogen for most of you, there's an old saying in chemistry that for every nitrogen, we add about 6 months extra to our Ph.D. So in order to avoid that, we want to find simple and efficient ways, and also ones that are safe, to insert into pharmaceuticals. So this is what I do in my research. So I start with two compounds that are derived from pine trees, and they are called camphor and fenchone. So these are terpenes, and what's important about them is that they are very cheap at about only $20 per kilogram. And they also have a very pleasant aromatic like pine smell. So through a couple of steps that I won't go into detail about today, I'm able to convert these compounds into structures that we call oxaziridines. So basically an oxaziridine is a three-membered ring, like a triangle, that has one carbon atom, one oxygen atom, and most importantly, one nitrogen atom. So I can take the nitrogen atom out of these compounds and transfer it into other chemical systems. So in our lab, we get a lot of experience doing large-scale reactions, kind of like you would do in industry. So for this, what's most important is I was able to synthesize about 490 grams of one of my starting materials in one step. So this is really important because we don't have to worry about having our materials readily available, and this allows me to test hundreds of reactions of transferring nitrogen, all from one step. So in my research with these oxaziridines in the last 2 years, I've worked on 4 projects to show how we can insert them into various chemical systems. So my first 2 projects focused on inserting them into various magnesium compounds that we call Grignard reagents. And then more recently, I've worked on inserting nitrogen into zinc compounds. And the main kind of caveat with this is that we're able to do this without transition metals. So most importantly, when you take a drug, you want to make sure that there are no heavy metals that could be toxic. So I'm able to show that this transformation works effectively in 4 different situations without using metals. And so while I was able to understand how oxaziridines work in all kinds of reactions, what's most important is that I hope another scientist can take this method and use this as a one-step route towards the synthesis of a drug-like molecule. So I hope I've been able to show you guys that we can see chemistry all around the world. Thank you.